In the last section, we introduced the dependence on the concentrations with this reaction, this equation here in blue, which is on your sheet, so you don't have to memorize this. But delta G is the standard Gibbs free energy change plus RT ln of Q. All right. But we said now that if delta G is equal to 0, right, that means you have equilibrium. So if delta G is equal to 0, these two terms, right, delta G0 must be negative RT ln of K, right? Because at equilibrium, this Q, it becomes K equilibrium. It's the equilibrium constant, right? So instead of evaluating Q, right, this is the equilibrium constant. So this relates the equilibrium constants, at least at standard conditions, at 298 Kelvin, which is where all those equilibrium constants that were in your back of your textbook were for acid dissociation constant, base dissociation constants, solubility products. Those were all Ks at standard conditions, right? And they were, you can get those from delta G. They're related, okay? So if you can calculate delta G0, you can get what K equilibrium is for a reaction. Let's look at an example, number 13. Example number 13 says evaluate the equilibrium constant at these standard conditions of 298 K. For this reaction, nitrogen plus hydrogen goes to ammonia. Right? Equilibrium constants are all gases, and we're going to use the standard energies of formations. Okay, so the equation we want to use here is delta G0 equals negative RT ln of K equilibrium. Right? So first of all, let's figure out what delta G0 is. Delta G0, it's 2 times the ammonia. Here's the delta G's of formation here. 2 times the ammonia is 2 times negative 16.5, which ends up being negative 33 kilojoules. Okay. So now we can rearrange this reaction to solve for K equilibrium. So we'll divide both sides by negative RT, and then we'll take E to both sides. All right? We've done this kind of stuff before. We end up with equilibriums is E to the minus delta G over R, delta G0 over RT. Right? We just manipulated this top equation to get the second equation. And now we'll just plug in E to the minus 33 kilojoules, but let's turn that into joules. So that's 33,000 joules. And the reason we're doing that because we know that R is going to be in joules, and you have to put them in the same units. You could either put them both in kilojoules or put them both in joules. And that's 8.31, remember, joules per Kelvin, mole Kelvin, and so we multiply that by the temperature, 298. So the kelvins are going to cancel. The joules are going to cancel. That's good. So we just have a number here. And that number comes out to E to the minus, or E to the positive. This was, delta G was a negative, so this ends up being a positive. Right, because there's a negative sign here and a negative sign here. So it's positive 13.3. E to the 13.3, you plug it into your calculator, you get K equilibrium equals 6.1 times 10 to the 5th. So we got from a delta G0 to an equilibrium constant, right? Something that we're familiar with. Let's see if this will help us picture this relationship that we just came up with, that the standard Gibbs free energy change for reaction is related to its equilibrium constant. Its equilibrium constant. And we're going to look at this reaction. Liquid water is in equilibrium, this should have been equilibrium, with water vapor, right? Water vapor. And we know, for instance, that the equilibrium constant for this, right, the mass action equation for this is that K is equal just to the pressure of the water. So it's the liquid water. So it'll be the pressure of the water vapor. Right? The liquid doesn't enter into the equilibrium expression, remember, because it's a liquid. All right. So the equilibrium pressure is just the vapor pressure, and in this reaction, this evaporation, right? You know that, for instance, that the vapor pressure at room temperature at 298 Kelvin, or 25 Celsius, the vapor pressure of water is much less than 1 atmosphere, right? It's a fraction of an atmosphere. So this equilibrium constant is going to be much less than 1, right? Because this is much less than 1 atmosphere. So this is the natural log of something much less than 1. So this becomes a negative, 2 negatives. This becomes positive. So delta G is a positive number. It's a positive number for evaporating water, or water in equilibrium with the gas phase, the liquid in equilibrium with the gas phase. And when you think about this reaction, you've got something, a closed container, and you have a liquid in it, and and these are both at the same temperature. So there's an energy distribution of the molecules in the liquid phase, and there's an energy distribution in the gas phase. Right? And the higher the temperature goes, right, the more of the water vapor is able to go into the gas phase. Right? The more is able to escape, so that the bonding, the intermolecular forces that are holding it in the liquid allow it to escape. And you can rearrange this reaction to this reaction in this way, the way we did before. The equilibrium constant, all right, which is of course just the water. This is just the either the pressure of the water or the concentration of the water vapor. It's only the vapor that matters. That's the K. Is equal to e to the minus delta G over RT. And delta G, we said, was a positive number. So delta G over RT. So this is a fraction, less than 1. And you can see if delta G gets larger, right? As delta G gets larger, the amount of water, or the amount of vapor, if it was a larger reaction that involved something else evaporating, and there was a larger delta G, there'd be even less in the vapor in the vapor phase, less pressure in the vapor phase. So you can see that this depends on K. So as delta G increases to a different reaction, a different evaporation, this amount will decrease if delta G increases.